A book resting on a desk and a hockey puck gliding across frictionless ice share a defining trait. Both maintain their current state indefinitely. To change an object's velocity, to start it, stop it, or turn it, requires the application of an unbalanced force. These principles of motion were first codified in 1687, when Isaac Newton published his Mathematical Principles of Natural Philosophy. Newton's first law defines inertia as an object's tendency to remain at a constant velocity. This resistance to change is an inherent property of all matter, and it is measured by the object's mass. The more matter an object contains, the more it resists acceleration. Determining if the acting forces are balanced or unbalanced reveals the object's entire trajectory. If the net force is zero, the current motion continues. If the forces are lopsided, the object must accelerate in the direction of the stronger pull. Newton's second law quantifies this change in motion through the equation F equals ma. This shows that the net force acting on an object is the direct cause of its acceleration. If you take an object, half its mass, and quadruple the applied force, the acceleration compounds. The lower mass doubles the acceleration rate, and the higher force quadruples it, resulting in a final acceleration 8 times higher than the original state. Calculations require a strict distinction between mass and weight. Mass is an intrinsic scalar property measuring matter in kilograms. Weight is a gravity-dependent vector representing the downward force exerted on that mass. On Earth, where gravitational acceleration is 9.8 meters per second squared, a 10-kilogram mass is pulled toward the center of the planet with a weight of 98 newtons. On the Moon, that same 10-kilogram mass still contains the same amount of matter, but its weight drops to roughly 16.3 newtons. The mass is constant, but the environmental force has changed. Confusing these two units leads to calculation failure. Mass in kilograms describes what an object is. Weight in newtons describes what gravity does to it. Newton's third law states that every action produces an equal and opposite reaction. These paired forces do not cancel out because they act on different bodies. If you push forward on a box, you feel the box pushing back on your hand with the exact same magnitude. We use a free body diagram to isolate these forces. For a stationary block, gravity pulls down with a weight vector, while the surface pushes up with an equal and opposite normal force. This isolation technique is required for multi-body systems, like the Atwood machine, where two different masses are linked by a single rope over a pulley. Because the masses are connected by the same rope, the tension force pulling up on each block is identical. However, the lopsided weight vectors pointing down create an imbalance that forces the system to move. To find the shared acceleration, we look at the system as a whole. The net driving force is simply the difference between the heavy weight and the light weight. By dividing this net pull by the total mass of both blocks combined, we arrive at the system's acceleration. While formulas summarize results, the underlying free body diagram is the only reliable way to track how tension and gravity compete within a complex system. When objects collide, we track their linear momentum, the product of mass and velocity. In an elastic collision, the objects bounce apart and conserve kinetic energy. In an inelastic collision, the objects deform or stick together, moving as a single combined mass after the impact. Momentum is a vector quantity, making sign conventions essential. If an object is moving right and bounces back to the left, its new velocity must be assigned a negative value to account for the change in direction. Friction provides the final resistance to these motions. Static friction builds to match your applied force exactly, keeping an object locked in place. Once the push is strong enough to break those surface bonds, the resistance drops to a lower, constant level known as kinetic friction. Introducing wheels changes the dynamic to rolling friction. By reducing the surface contact area, the force required to maintain motion drops to its lowest physical level. Engineers minimize these forces through the use of lubrication, ball bearings, and streamlined designs that reduce the drag of the surrounding air or water. From the hidden tension in a rope to the subtle friction of a rolling wheel, the motion of every physical object is the predictable sum of the forces acting upon it.